Okay, good morning, everyone. We have, first off, I have to say here, if I look like I shrunk over the weekend, it wasn't a quals exam. The chair is broken up here today, so I'm way down at the bottom here, but hopefully we'll be able to write with the pad in the face here. The homework will be due on Thursday. Don't forget the feedback question at the end of the homework we'd like to get each week. So that's problem set number one, of course, the first one. Probably feedback is most helpful on that first set. Let me just ask, is anyone having any administrative problems? Any new types of things that have come up? I know that there's some registration issues. I think some of those have been resolved so far. Anyone still having trouble registering for the class? No, we seem to have that under control then. We will then proceed really with today's lecture. I don't have any handouts for today, but what I would like to do is just begin with kind of a review of what we covered last week before I branch off into today's lecture. We're basically going to be in section 1.3 of the notes today if you're following along in the syllabus. What we talked about last week, just by way of review, was both the modulator and the demodulator. The modulator, if I were to draw the entire system kind of together, the modulator basically took vectors. We had a set of capital M vectors, which you call data symbols, that represented messages to be transmitted. And those n-dimensional vectors, which were dependent on the message to be transmitted, had each element of those vectors multiplied by a message-independent set of basis functions. And basically we create analog signals this way, we add them all together, and different types of basis function sets create different types of modulation systems, as well as the actual selection of data vectors, the dimensionality that we use to represent what's sometimes called the signal constellation, which is a set of all possible data symbols, each one of which will represent a message. And that modulated signal is x of t, continuous time, or analog, if you will, and it is what we, of course, need to have in a physical world where everything is analog. And we transmit it through some kind of channel. We call the output y of t. And then we had a demodulator over here on the receive side, which is after the channel, of course. And what we postulated really last time is certainly true if there's no distortion in the channel. But we postulated essentially that we wouldn't lose anything if we went through this set of what are called match filters and sampled each one at time capital T, where capital T was the symbol period. It was the time interval over which we send each message through the channel. And we would produce over here at the output, in the absence of any distortion in the channel, we clearly produced the original signal vector back, so we could proceed to then decide which message had been transmitted. In the presence of distortion, it's not necessarily a guarantee that this particular receiver structure necessarily contains all the information about what was transmitted, but we could nonetheless do it and proceed to make decisions on whatever we got out of that structure, and proceed to design a transmission system for that. So we're going to come back to noise today, but this is review here. So we had this vector channel last time, and essentially we had this nice diagram now where you just have x, the vector of inputs, going through some kind of probabilistic description of the channel, probability of a vector y on the output, where now in the presence of noise, really this becomes y1, and this becomes yn up here at the output of the channel. So we call that vector y on the output. And then the question that we looked at on Thursday was, okay, we have y. Now which x was most likely to have been transmitted? And the one that was most likely to have been transmitted is the one that minimizes the probability of error. So we go through some kind of device, often called a detector. We can call it decision device, and decoder sometimes, all being used interchangeably. And we're going to try to decide which message was sent. And a probability of error, of course, is the probability that the message that we decided is not equal to the message that was actually transmitted. And so that's the same as saying probability that the x hat here at the output of the channel is not equal to the x at the input of the channel. And good receiver designs minimize that probability of symbol error in transmission. And we saw a couple of very good designs last time. So this vector channel replaced the original channel. And the one that actually minimizes the probability of error is called the maximum a posteriori detector. And it basically reduces down to this. X hat is selected at as a particular message, x of I, if, and only if, the probability of y given x for the received value that we actually got at the output of the channel, we'll call that v, be strict in the mathematical sense. We shouldn't put y and x inside the parentheses if we have them here on the subscript. That has to be the largest, and p of y given x v j for all j not equal to I. Now, actually described here was the maximum likelihood detector. This is a maximum, this is a likelihood function, and we're just picking the maximum, which is why it's called that. If I want to do the map detector and the inputs are not all equally likely, then I have to stick in a multiplicative factor, which is the probability of the input distribution itself. And so that may alter this decision slightly. Yes, sir? I'm sorry, there's like a fan in the ceiling here. I'm having a real hard time hearing what you said.
Just asking if this is the type of thing that you compute beforehand, or if it's something that you'd be computing on the fly as you receive the data.
Well, you could do it on the fly. You can do it both ways. And in fact, the next point I was about to make in review speaks directly to your question, which is if you wanted to kind of pre-compute, you could do that. And in fact, we had this concept of a decision region, which really is the pre-computation of the decision for each and every possible value of v. So you're right. I certainly know what the range of v's might be at the output of the channel, and for each one of those I can pre-compute what the maximum likelihood decision would be. And I can take my space, let's suppose it's a two-dimensional space, and I may have some weird type of boundaries depending on the probability distributions, but I may have all points in this region being, let's say, message 0, all points in this region 1, and maybe M2 and M3 over here, like that. And that's an example of pre-computing, really, the decision regions. Any other? Yes, ma'am. The Minimax theorem often I find confuses a lot of students, confuses me also. It's got some conditions in it that are necessary to happen. But basically, it's a kind of a hand-waving justification for the use of the maximum likelihood detector in place of the map detector. And what it says is, under some mild conditions, that if you don't know what the input probability distribution is, that assuming it's uniform minimizes the worst case probability of error you could get for a detector. So in some sense, it's still good even if you don't know the input distribution. Now, there's some symmetry conditions that are in that theorem that don't always apply. And so it, in some sense, is kind of a digression from the main event, which is either, if you really do know what the input distribution is, choose the map detector, and if you don't know, you're pretty much stuck with going with maximum likelihood anyway, even if that didn't quite minimize the maximum deviation of the probability of error. It's pretty much the only thing you can do if you don't know the input distribution, is to assume it's uniform. Any other questions? Okay. Well, what I would like to do today is in some sense try to go back and justify that additive that demodulator that we just showed in class was in fact a good thing to do. In fact, it's the optimum thing to do for the additive white Gaussian noise channel. In order to get there, we're going to go back to the irrelevance concept that we had at the end of Thursday's lecture. And in particular, we're going to look at the reversibility theorem. And then we're going to proceed to define the additive white Gaussian noise channel, and then look at specifically what is the form that the ML and MAP detectors take on for this type of channel. So we're going to get a specific type of channel today. It's going to be an easy one. All we're going to do is take the original signal, transmit it through the channel, and add some noise to it. And that noise is going to be Gaussian in distribution. And it's also going to have a property, white, which simply means that at any point in time it's uncorrelated with itself at any other point in time. And we're going to see, in fact, that for that type of channel, the demodulator that we've designed is indeed optimum. And in fact, that's a very common type of channel to see in practice itself. And we're going to start talking near the end of the lecture about the probability of error calculation. Now that we've minimized the probability of error, okay, great, we got a good receiver. How good is it? Okay, we haven't really addressed the issue. How often is it making errors, even if it is the best thing that we can do? Is that good enough in the transmission system? So those are the topics we hope to hit today. Now, by way of review of reversibility, I'm going to draw it, irrelevant components and reversibility. What we look at is a channel has some input X, and we decompose the output into two parts. And we say we can throw away one of those parts if certain conditions are met. The overall received channel output is really Y1, Y2. And so when can we throw away Y2? Well, we saw in the last lecture, basically, that there was a condition that if the conditional probability of the input given both of the output components is equal to the probability distribution of the input given just one of those components, then you can throw away the second component. Now, there was an equivalent way of writing this theorem, which was that maybe a little more obvious, that the probability distribution of the second component of the output given both the input and the other component of the output is independent of the input. Then you can just throw away Y2. Don't need it. Doesn't contribute anything to the MAP detector if that condition is met. Now, reversibility is kind of a nice theorem. We'll use it more and more as EE379A and some of the subsequent classes go on. And so it's a nice concept to kind of have buried in memory somewhere, even if you don't see us using it immediately here today. And that is that if we send a message through a channel and we call the output of that channel Y2, and we run through any transformation whatsoever, let's call it G, that's 1-to-1, so it's reversible. If I know the output, I can reproduce the input. Let's call that output Y1. Then basically, by the conditions of the theorem that are written right above, we can see here, probability of Y2 given Y1 and X, since this is reversible, well, clearly that's the probability of Y2 given Y1. In fact, if I know the value of Y1, then I know immediately what Y2 is. It's kind of a delta function. The probability is 1, that it's G inverse times Y1, okay, or G inverse of Y1, if you will, and not anything else is got zero probability of occurring if I actually know what Y1 is. So I don't need to know X if that's reversible. So that's kind of a trivial statement. Now what this really means, okay, why do we say this? Well, I may decide that it's easy in my receiver for some reason to take a function g, take the output y2, and then map it into some other output, y1. And it may be a lot easier to design a receiver for y1 than it is for y2. It may have more convenient decision regions. It may be simpler to implement in some sense. And as long as this transformation is one-to-one, I know fundamentally I haven't lost anything in my receiver with respect to a best decision. So it may well be that y1, we could actually think of it as going this way, where we would actually go through G inverse, okay, and now we're back to y2, and I would have a map detector for, let's say, y2 here. This whole thing here is a map detector for y1. And one of those two may be easier to implement. So that's a theorem on reversibility. Kind of falls out trivially as part of this irrelevance theory. And it may be something that we'd like to use later in the course. Okay. So that's irrelevancy reviewed. Now what I would like to do today is to proceed on additive white Gaussian noise. So that's topic 2 for today. Now we will see this channel almost exclusively in transmission theory, the additive white Gaussian noise channel. Why is it used and what does it look like? Well, let's go back to continuous time for a moment. What happens is that the signal x of t, this analog or continuous time signal, passes more or less, let's say, without any distortion through a channel. What that probably means is that the bandwidth of the channel is much greater than the bandwidth of the modulated signals. Okay, it's never possible to actually have a true impulse response for a channel. But if your channel kind of looks flat, if you will, in its transfer function, everywhere that you're transmitting signal energy, then the signal energy is going to pass through pretty largely undistorted. But it's almost never true that we'll see no noise in a transmission system. Every transmission system has noise, maybe small, but it's never zero in practice. And that's all that happens in the additive white Gaussian noise channel, is that noise is added. Now this particular noise here is zero mean, and it's stationary. So basically its probability distribution doesn't change with time, and it is Gaussian, as you could guess from the name, in distribution. Gaussian distribution, we just write down those terms in a little more formal way. E in this class means expected value. So you should have seen that in your probability courses. And basically, we're saying that this noise has an average value of 0. Most noise typically does have an average value of 0. If it has some other average value, no problem, just subtract it off if you know what it is, and then you'll have something that contributes nothing and detracts nothing from transmission if you have an average value to noise. So we can pretty much always get away with assuming it's 0, even if it wasn't, if we knew what it was, or we just measure it and then subtract it in the transmission system. The probability distribution, that Gaussian distribution, in case you've forgotten from your probability classes, looks something like this. If the Gaussian random variable is real, then you're going to get 1 over square root of 2 pi parameter sigma squared. It turns out that parameter is the variance of the noise if you actually do the integral for the variance. U squared over 2 sigma squared. So it's an exponential type of distribution. Decays very rapidly for large U values, either positive or negative. It gets to 0 quickly. So if you were to draw a picture of it, small values of noise are very highly probable, and then larger values of noise are increasingly less likely. So that's a reasonable assumption to make perhaps for noise. Now, why Gaussian? Okay. Well, it turns out that this is not only a nice thing theoretically, but something that also pretty much holds up in practice. And one of the reasons that well, let me see if we can get some takers on it. Anyone want to tell me why noise, generally speaking, might be Gaussian? Yes, sir.
Noise comes with hundreds of thousands of sources, and something like that makes it Gaussian.
That's right. That's exactly what's happening with noise. So Gaussian's a pretty good distribution because typically if it is noise, it's some kind of random thing coming from a lot of different sources. So we all remember the central limit theorem. It says if we add a lot of random variables together, we get Gaussian distribution. So that's a fairly good assumption to make in most transmission systems. And in fact, if it wasn't Gaussian noise, if we had some other kind of noise, there's probably some intelligence in that noise that we could exploit. It really isn't completely